Okay, so welcome everyone, my name is Phil Winder and this presentation is called the Industrial Applications of Reinforcement Learning. I'm the CEO of Winder Research, which is a data science consultancy based in the UK. We help medium to large size companies industrialize and productize and operationalize data science. And as part of our work, we have been very interested in reinforcement learning. And the reason for that, oops, if I'm on the right screen, is because I've just literally a few days ago finished my first book for O'Reilly. It's a book on reinforcement learning. The whole goal of the book is to try and take a lot of the inspiration that I saw from academia, a lot of the examples, a lot of the algorithms, and try and bring them into industry a little bit more, because there are lots of examples out there and there are some really great use cases, but there hasn't been much adoption in industry yet. So this book is an attempt to try and bring some of that academic knowledge to industry. I'll put this link on at the end again, but yeah, if you're interested, you can go to rl-book.com. So this is a presentation about all of the applications that I came across whilst writing the book. Okay, so the first question is, and let me do some judicial pausing here. The first question is always, well, Phil, what is reinforcement learning? You know, I'm dealing with Java code most of my day. I haven't really heard of reinforcement learning yet. So learning by reinforcement is a really fundamental process, and it's best explained in relation to animals and humans. It describes how we learn as humans. I've got a couple of chickens in my garden. I've got Bella and Charlie, and they're getting a bit old now. So Bella is a bit of a freeloader. She doesn't lay many eggs anymore. Charlie's still okay. But you know, the thing that surprises me about chickens all the time is that they're actually quite smart. And this is an experiment by a couple of researchers that are attempting to train a chicken to peck at a specific dot. So you can see that the chicken has kind of started to peck at this pink dot on the table. It may not have done that initially. It may have walked around. It might have jumped off the table or pecked around a bit more. But eventually it will peck that dot, because they are quite inquisitive creatures. Whenever the chicken touches that dot or pecks the dot, the researcher there, she gives him a reward. Gives her a reward. And this reward, that corn, is reinforcing the behavior that we would like to see from this chicken. So we're saying to that chicken, every time you peck on that pink dot, we're going to reward you positively, so that next time hopefully you'll remember that that's a positive action, and so you're going to repeat that action. And you can see the other researcher, the lady on the left there, she's making it increasingly complex by adding all sorts of different colours, all sorts of different dots, and yeah, eventually it's quite difficult for the chicken, but still chickens are quite unique in that for such a small animal, they can see in full colour. They have a full, yeah, they can see all colours like we can, so it's unlike dogs and things like that. So it's quite easy for the chicken to distinguish this pink dot and you know, receive the reward. If you just saw, I'm just going to pause it there, the lady just moved that pink dot whilst the chicken was turning around. And if you just watch now, if you saw, the chicken actually went for the wrong location there. It was predicting where the dot should be, and it wasn't. And so it pecked anyway, and it won't receive a reward now. So it's not being rewarded for that behavior, because that's not the behavior that we're trying to train in this animal. Okay? And there you go. And now the hen has run across and touched the pink dot again. Okay? So this is it in a nutshell, really. This is trying to encourage certain behaviors through reinforcement. And it started quite a long time ago. So these are some, I'll just pause this video. This is a video from R.F. Skinner. This is about 50 or 60 years ago, where he trained pigeons to read signs. He was trying to show that they're, you know, reading words is not necessarily an intelligent thing to do. And what he managed to do is, through reinforcement, he trained pigeons to perform certain actions. So we've got a sign up at the moment that says peck, so it's pecking at the sign, and it receives a bit of corn, and again, it reinforces that behavior. There's a sign there saying turn, and the pigeon now turned around, and again, received a reward for reinforcing that behavior. So again, another example of learning by reinforcement. All right, so we like chickens, we like birds. Are they going to take over the world? Well, there's a lot of nationalist sentiment going on at the moment, and that also extends into the animal world. So this is a Spanish chicken, and this Spanish chicken really likes Spain, and so he will only peck on the Spanish flag. So I'm sorry Switzerland, I'm sorry France, I'm sorry Czech Republic, I'm only going to peck on the Spanish flag. Same thing again. And I think that there is a potential for chickens taking over Spain, and when they do, hopefully you can see this video because it's amazing, they're going to raise the Spanish flag in the new chicken state. I like his t-shirt as well. My chicken is more intelligent than your dog. Very good. So the point is, anyway, I like her response as well. Not that impressed. So that is learning through reinforcement. So I just wanted to demonstrate what learning through reinforcement was. So how does that apply to industry? How can RL help industry? So when I think of businesses in general, there are three kind of distinct actions that a business has. You can call these sort of operational business activities. There are processes, decisions, and strategies. So at the low level, at the bottom, there's processes, and there's many processes throughout all businesses everywhere. A process could be onboarding a new customer, or it could be connecting your laptop to a printer. That's an example of a process. Higher up in the hierarchy there, we have decisions. There's fewer decisions, but they're very important because they typically decide what business happens when. So, for example, a decision could be to decide whether a customer gets a loan or not. And then finally at the top, we've got strategy. And these actions are few and far between. There's typically only a few people that ever define a strategy in a business. And when they are defined, they have impacts all the way down. They define the decisions, they define the processes. Okay? We can view those in terms of cost as well, or value, depending on how you look at it. So generally, processes have very little value. Connecting your your laptop to a printer has very little value. It needs to be done, but there's very little value in that act. Decisions are quite valuable because they usually involve, customer-centric decisions, like giving a person a loan or not, so you could make money or lose money. Strategies entirely define businesses. So again, these are possibly the most valuable decisions to be made within a business because they could either make a business successful or not. And we can map these three layers to different technologies. At the bottom layer, we generally automate processes with simple checklists, simple reports, simple things like that, sometimes software. Software is really good for encoding business processes. We can automate decisions with machine learning. So whenever there's a decision to be made, a one-shot, a single decision, we can automate that with machine learning. But strategies on the top there, machine learning struggles because strategies involve multiple decisions over a long period of time, so it's hard for them to optimize, and that's where reinforcement learning comes in. Reinforcement learning automates strategic decisions. So what do you need to do RL in an industrial project? The basis of reinforcement learning is all built upon something called a Markov decision process. It's a mathematical formality, but the Markov decision process, which is abbreviated to MDP, effectively defines a framework in which you can define your problems. There are two entities within an MDP. There's an agent and an environment. So the agent is the thing that actually enacts and actually decides upon what actions to take within an environment. So let me give you an example. Imagine you are learning to ride a bike, and you are the agent in this scenario. You're learning to ride the bike, and you provide actions to an environment where the environment is the world around you, the grass, the wind, the feel of the bike, things you can see, things you can hear. That's the environment that you are learning to ride the bike in. So I've just mentioned it a few times there, but the agent is responsible for generating actions within that environment, like turning the handlebars, pedaling the wheels, things like that. that mutates the state of the environment. So if you pedal, what you could see previously is now no longer valid. You see this new, if you've fallen off your bike, if you've crashed, you see blood and pain, and, the environment has changed. Okay, and that is represented by the state that is emitted from the environment. Every now and again, the environment also emits a reward. And this is the thing that encourages this learning by reinforcement. A positive reward is telling the agent, you should do those actions again. A negative reward is saying, don't do these actions again. So if you're learning to ride a bike, you might get rewarded negatively when you fall off. So you will learn that you can't just turn your handlebars at 90-degree angle. You've got to do it slowly. Things like that. Okay, so now I'm going to go through a few examples, and I'm going to try and explain all of the different parts of the MDP within those examples. There's hundreds, probably more than hundreds, there's probably thousands to choose from. As I went through the process of writing the book, I came across them, and I attempted to start cataloguing them and creating a database of them. So this is one of the pages on the RL Book website, and I've collected a whole range of examples from various different industries, but I can't go through all of them today. So if you're interested in a particular industry, then I recommend going to that website. I picked a few that I thought were really cool and would work well in a presentation like this. And the first couple that I'd like to talk about is about manufacturing. And when we say manufacturing, generally what we mean is using robots to do manufacturing. Okay, so there's lots of really good examples of using reinforcement learning to train robots to do things within manufacturing. So let's dig into some of those examples. All right, so we've got another video here, so I'm going to try and pause it so you can all see what I'm talking about. Okay, so the first example we've got is quite a generic one. This is a commercial robot that is sort of designed after a dog, and the manufacturer provides a very small number of preset movements that the robot can take. So these researchers set out to ask the question, can we learn more dynamic and more interesting movements by copying real life? So what they did is they looked at real animals, they looked at a real dog, and they attempted to copy and clone the movements from a real life dog, and then train a robot using reinforcement learning to mimic and reenact those actions. All right, so let's just let that play now. I appreciate the frame rate's not very good for you. The whole idea is that designing some of these policies, designing some of these strategies to do things like have a backwards trot, like that was what that series of images were, is incredibly difficult to code by hand. It's even very difficult to use machine learning for because the actions that you have, which in this case is the movement of the motors, can have quite long-term effects. If you have a bad leg movement 10 seconds ago, that could cause you to fall over 10 seconds into the future. So you need to optimize and reinforce behaviors as opposed to having this one-shot, myopic view of movement. So here's like a super slow-mo. It'll be really super slow-mo for you guys of doing like a hop turn. And you probably can't quite see, but there's a range of really complex movements that are involved in creating that hop turn. It's not just one single action. It's many minute little actions. And then there's some more examples of what happens when it isn't trained properly and it falls over. So in this case, the environment was what you can see in that video camera. The actions were movements of the motors within the legs. The state that represents the environment were things like the positions of the motors. There's like accelerometers and things on board as well. And the reward in this case would be like moving forward and moving forward fast and also not falling over. So you design these rewards in order to produce the strategies that you're interested in viewing. Okay. Next example is it's not quite as interesting from like a visual perspective, but it has some really unique features that I wanted to show. Previously, we had a state representation that was motors and accelerometers, lots of really low-level, detailed information. This is a robot which is being trained to turn a valve. So you can imagine in like an industrial setting on an oil refinery or something like that, the robot will go up to a valve and be told to turn that valve to a specific position. So what the researchers did is they are not relying on like raw feedback anymore. The only state in this example is this video camera. This is the only thing that is being used to train this robot. Okay, so this is all of the exploration that's going on. It's going really fast on my screen. But obviously it's quite slow on yours, and I'm just going to wait until it gets to a valid policy. Here we go, somewhere about here, and I'll stop it. So what it's learned to do, based upon the goal was to try and move this valve into a specific position. The researchers generated just a few examples of what they wanted the video camera to look like, and the robot, by itself, has learned how to turn that valve to the final position that you can see now, without any interaction with the human at all. And it doesn't even know where its limbs are. All it's doing is just randomly flailing about and using this visual information to be able to learn what to do and how to move and how to eventually move this valve into the right position. So I think that's really fascinating. It's not a fantastic. I wish there was a bit more of an exciting example, and I'm sure there will be soon. This is quite new research, but this is one of the first examples of learning sort of end to end, only using a video camera to train a robot. It's remarkable. Okay, this one is a lot more fun. So one really tricky task in reinforcement learning is to teach robots that have large numbers of motors and large numbers of limbs. This is a simulation of two humanoids. So they're humanoid simulations. And one is being trained to try and score a goal in football or in soccer, and the other is being trained to stop the ball from going into the goal. He's the goalie. Okay, so the blue is trying to score a goal, the red is the goalie. I'll try and stop it at a good frame. So the blue comes up to the ball, and we saved it that time. There you go. So that one went in the net. So that's all really cool in and of itself, and that's actually quite a hard thing to train for, because there's so much exploration that the robot or the simulation, the agent in the simulation, needs to do in order to generate all of these policies to walk, to kick the ball, to stand up straight, things like that. But this research is really cool because they're investigating adversarial strategies. So when an agent has been trained on a particular data set, it's still using data. It is generated by it's generated through exploration, but it's still using data to train upon. When these strategies are tested against situations that they haven't been trained upon, strange things happen, just like in machine learning, same thing. All right, so in a minute, what the goalie is going to do is do things just like randomly fall over. And you'll see, I'll try and stop it, but now the blue agent is having a really hard time trying to figure out what to do. It doesn't really know what to do, and in fact, it starts stumbling around like, it's drunk and, just come on, refresh. It's like a drunk football player trying to kick a ball. You see how it's doing a bit of a dance, and it fell over. So this is an example of adversarial strategies in order to, try and affect the other person's strategy. So that's really fascinating, but let's get on to an actual real life situation. So in a factory in Berlin, there is a robot provided by a company called Covariant.ai, and this is a very common. I'll just pause the video again. This is a very common example. It's a pick and place robot, and what it's trying to do is it's trying to pick something out of one tray and place it into a box for delivery. Typically, robots are used in kind of different formats because of the complexity of picking up objects. But in this case, we've got a single robot picking all sorts of different products up. So I'd just like you to sort of concentrate on looking what's in the box. And hopefully you can see there's lots of different types of shapes, lots of different colours. Oh, I've got none of my boxes. There you go, a small orange one, a big blue one. Let me try and, yeah, there you go. There's like a green sort of square-shaped box. You see there's some tape there. Most robots would really, really struggle to pick up this diversity, this sheer number of different types of object. But because this has been trained with reinforcement learning, it can over time learn to pick up a huge variety of objects. And yeah, again, let me explain the different parts of the MDP. So the environment is real life this time. It's a real life factory. The state, again, is like position of the motors. I think it's got a camera in the picker as well. The action is control over those motors. And finally, the reward is picking up something and placing it in the right box at the right time. So that's been trained with reinforcement learning to generate some you know, pretty cool performance in a real industrial application. Okay, let's just do a time check. All right, so that's 22 minutes. I think we're okay. This is another example now from tech. Oh, and actually I've just realized this is a GIF, so I can't even pause this one. So I might skip back to this screen. So this is an example from the tech industry. The idea here is that we're training an agent to perform very common sort of back office tasks on HTML-based interfaces. So this is one particular example of an inbox, like a very simple stylized HTML email inbox. On the left-hand side there, you can see that there's a list of messages from people and things. And the agent can actually interact with this HTML data through things like CSS selectors. So it can actually click on buttons and it can actually pull out data. What these researchers were trying to do were trying to automate some very common tasks, and this is one of those common tasks. The idea is, from an email inbox, we want to forward an email from Bob to Alice. So the first state is the email inbox. The first action is to click on the email from Bob. The second state is the actual email, and then the second action is to click the forward button at the bottom here. The third state is like a new email box, and then the third action is to type the word Alice, and then the fourth state is the same new email but with now Alice in the top, and then finally the final action is click send. So you can see that there's several distinct and sequential decisions that need to happen in order to fulfill the task of forwarding an email from Bob to Alice. And the cool thing is that reinforcement learning is perfectly suited to optimize these sequential decisions. That's exactly what they're trying to do. So through the interpretation of this HTML state and via the actions that we're able to click and write text and stuff, these researchers managed to train an agent to fulfill many of these tasks. Now, it's going to be a bit difficult here. I don't quite know what it's going to look like for you lot, because I can't. These are GIFs, and unfortunately I can't pause the GIFs on this. But basically, on the left-hand side, we have a range of example tasks in the yellow box. It says things like find Kirby's email and say something in French, I think. I won't try and say it. And the agent has learned to click on the new email box, type the text, type in the person that it's supposed to be sent to, and then click send. On the right hand side, we have a similar set of tasks, but this time it's more like a sort of Twitter-like interface. The tasks are like, for the user Kristin, click on the report button. So the agent has learned to find the user called Tristan, click on the 3 dots at the side, and then click on the report button at the end. I really like that example because this is something that most people are kind of interacting with on a daily basis, and I think it's very easy to see the power and the potential application of automating some of these generic tasks that we do on a day-to-day basis. All right, one more quick example, and some of the examples that I'm very interested are related to energy. Okay, the problem is that there's not many good, videos or demos of like hot water tanks. Unfortunately, heating a hot water tank is actually quite a boring thing to do, but it is vitally important in terms of improving the situation with climate change. I think that I read the other day that 40% of the EU's energy is spent on energy that powers and lights and heats our homes and buildings. So if we can just make a small improvement to some of the efficiency of some of these buildings, then it translates into a huge amount of savings in terms of carbon emitted. One of the parts of this is transport. And if we can improve the way in which vehicles are travelling, not just the underlying technologies, obviously, for burning fossil fuels, but the way in which they get from A to B, again, there's huge potential savings in here. So there's a lot of research going on at the moment for things like traffic management systems. One of the biggest problems on larger roads is the concept of queues, and queues specifically due to work being done on the road, or maybe an incident. Because with those in place, there's the largest source of secondary incidents after that kind of blockage is due to just poor control and poor driving on the behalf of the driver. So what a lot of the research is trying to do at the moment is to find neat and interesting ways of basically controlling the traffic so that they can drive optimally. So this is quite I'll pause the video here. This is quite a complex picture, but this is a reinforcement learning application where the state is the current position and the velocity of all of these vehicles. The action is telling a specific vehicle to travel at a certain speed, and the reward is basically the flow rate of the cars. And so what these agents can do is optimize to basically tell the car to go at a very specific speed so that in the future another car can merge into that lane successfully. And overall throughout the entire system you've got the maximum flow rate you could possibly have, reduced crashes due to slowing down and speeding up, reduced fuel usage, and so on and so on and so on. So this is kind of the direction that so-called smart motorways are going in, but they're not quite there yet. I think with a few more years and a few more improvements to the way that the signage and the cars are controlled, I think this is definitely going to be an interesting set of applications. All right, I've been talking for about 30 minutes there, so I'll begin to stop, but I'll just finish back where I started. This has all come from my new book, Reinforcement Learning. It will be coming out. The best estimate for the release date is the 1st of December at the moment, but it very much depends on how quickly the copywriters and the editors can get through all of their processes. So in the meantime, what I'd recommend you do is go to the website rlbook.com and sign up for notifications there, and I'll send you through. The next thing I've got to do for this is go through and fill in all of the examples and all of the worksheets and everything that needs to accompany the book. So sign up there and I'll send all those out to you, and I'll let you know when the book is released. And then finally, if you've sort of been inspired by some of this, or maybe you've had some thoughts about how you could use reinforcement learning in your work, just send me an email. I'll be very interested in hearing what ideas you've got, and maybe I can help out there as well. So that's winderresearch.com. Okay, I'll stop there and I'll just take a breather, and I'll hand it back over to you for a few minutes to see if you've got any questions. Thank you very much.